Good morning, everybody. Welcome to another edition of our Power Hour. Today, we'll be talking about DNP3 basics. Just want to kind of let everyone know the emphasis is on basics. So it's not advanced, it's basics. And the idea behind this is that in my past life, I used to do DNP3 training. It's usually about 3 days worth of training. And so today, I'm not trying to condense 3 days worth of information into 1 hour, but is to provide everyone here in the webinar just to some terminologies that you might have seen while working with DNP3. If you're new to it, or even if you've been using for a while, you want some clarification or just kind of better understanding of the protocol. We're not going to talk about advanced features. There is advanced features that we implemented, such as secure DNP3. That might be in the future Power Hour. But today we'll cover the kind of high-level basic overall of the protocol. I myself, Chi Carnegie, is one of the presenters today. Joining me will also be Brett Dolgen and Jamie Larson. For the agenda today, just basic high-level history, what kind of points and data you can use to with DNP3 to pull in your system. Within the protocol, there's terminologies as object types, what type of polling schemes you can do, protocol layers. We'll dig deep into the message structure of DNP3 and what you can kind of look for when you're troubleshooting. To end the Power Hour, Jamie and Brett will be doing a live demo of different configurations in NCD for DNP3 client and server. All right, brief history. In the olden days, early SCADA, before SCADA protocols really was implemented, to get information on your system, everything was wired. Even today, there's I/O modules, but back then, everything was wired to be able to get data for your system. Even if there was a communication protocol, it's usually proprietary to specific devices or vendors. And it was kind of kept secretive. But in the mid-1980s, there was a push for more of an open standard to help with different devices to talk to each other. So there was a need for a standard-based protocol. That being said, in 1990s, and I'm very, very proud of this because this is where I grew up, DNP1 and 2 was invented in Calgary, Alberta, Canada. It was invented by a company called Westronics, which later became Harris Westronics, GE, and then GE Energy Management. In 1993, became public domain, so it became open to the public and started a user group. So DNP3 is an open standard. You can join the user group today if you want to. There's a technical committee that later got established in 1995. In that committee, created testing certification procedures and so on. So at the end of the day, it is a standard, and any device that's considered to be a DNP3 supported device needs to pass these tests in performance procedures. All right, so very quick overview, kind of SCADA 101 basics. I just want to kind of provide a high-level terminology summary. So this is kind of a basic SCADA architecture. This might what it looks like in your substation. And usually we have a data concentrator, and you have some relays, some I/O modules, some meters maybe. You need data from these devices. And so the terminology I will be using a lot today is server. So how I always like to remember this is if a device is serving up data, it is a server device. So these are considered to be DNP3 server devices. And in this relationship here, the Orion or the data concentrator is acting as a DNP3 client. You're a client, you want something, you're going to ask for something. So that's how I remember it. In this relationship here, is kind of different because the control center, your SCADA center, EMS, so on, will be acting as the client. So it's going to be requesting, polling, and then the data concentrator or the Orion is going to act as the server. We're going to be the DNP3 server that serves up the data. In older documentation, you may hear the term master and slave. We're moving away from that, or there's also a term it's called outstation for the server side, so you might see that in some other documentation. But within NovaTech's documentation in the last few years, we've changed everything from client and server. This applies to all the other protocols that we support. In our NCD configuration and documentation, you'll see that there is a client side and a server side to a protocol. So that's just some kind of brief terminology that we'll be using today. Very high level overview of what data you're getting. So within SCADA, you're always trying to ask for data. The data will help you monitor your grid. So some data such as binary input data. This could be your breaker status. Is it open, closed? Is it local, remote, on or off? So binary is a 1 bit that represents 2 states, 0 or 1. Within DNP3, depending on some application, there might be 2-bit binary input, and that is to convey 4 states, 0, 0, 0, 1, 1, 0, 1, 1. 0, 0 can be your open, 1, 1 could be your closed, and the other 2 state could be your travel state or your error state, just to allow more information for that binary input. Analog, obviously these are numerical values. It could be your current, your voltage, frequency, temperature, depending on what you're reading. It could be 16-bit value or 32-bit value, depending how big the number can get. For counters, it counts. Very self-descriptive. At the end of the day, it's usually or another term for it is accumulator. It counts up, starts from 0, and it counts up. It could be monitoring, let's say, how often this binary input changes. It can count up, and then once it reaches max, for example, if it's a 16-bit counter, if it maxes out at 65536, then it will restart at 0. On the opposite side of that is outputs. So you got your binary outputs and your analog outputs. So for binary outputs, you're sending a bit value to your DNP3 server. It's usually a control point. It could be, open or close or breaker. Analog, you're sending a value to your DNP3 server device. It could be, a threshold, a deadband setting, tap changer position, whatever. So you're sending an analog value to your DNP3 server device. Within DNP3, there's 2 types of controls. There's direct controls and there's select before operate controls. Direct control sounds very self-descriptive there. It is very direct in the sense, hey, when you're a DNP3 client, you're sending a direct control. You're pretty much saying the 0 to binary input 3. Let's say that means could be represent open. And pretty much you fire that and then hoping your device receives that and operates based on that control. The more safer route is the select before operate control. It's a multi-step procedure. So before you're doing anything, you're actually saying to your DNP3 client, saying, hey, just so you know, I'm going to be sending a control to your binary input 1 soon. Are you ready, kind of thing. The device responds back confirming that it's ready, and then your server, the server sends back saying it's ready, and then the client will say, hey, I'm going to send a value of 0 to this point. So it's a select first, gets the confirmation, and then it operates. So these are function codes within DNP3 that I'll kind of talk a little bit later in the slides. All right, as anyone who's ever used DNP3, there's always address, or we always talk about pointless for SCADA. And so at the end of the day, similar to kind of address in your house, it's to differentiate your points, differentiate your houses. So the address or indexing is to differentiate the points within the specific point type. So analog input will have its own point list. Binary input will have its own addressing or point list, encounters, and so on. So DNP3 uses addresses to differentiate, not by name. Some other protocol uses names such as 61850, ICCP. So those are very specific name protocol. We use addressing. DNP is a zero-based protocol, so you can start with address 0 if you like. Within DNP3, it used to be when older devices, I've noticed that you need to be continuous addressing, but not anymore. What I've noticed is you don't have to be continuous. So when you're configuring, let's say, DNP3 server on the Orion, you don't have to have your point list be continuous. It can be, interrupted, sectionalized, or whatever. But it is recommended to be continuous if you want more efficiency in your data transmission. By that, I mean, if someone is polling the Orion, and if all the points are continuous, then you can just send the data back, just only the value. You don't need to send the indexing or the address with it, because if it's all continuous, it's easily read and assumed that it's in the right order and that it can parse properly. If your point lists aren't continuous, then the index has to be sent back with the data so that the receiving device knows, hey, this data represent binary input 1, this data represent binary input 7, for example. So that's just the reasoning behind if you want continuous point mapping or not. All right, object types. So within DNP3, there are, for especially reading input values, binary input, analog input, there's usually 2 types of points: static points and event points, or static types, event types. Static means what is your most present current value that you have in your database at the server side. Event means something of importance happened. For example, a binary input could be changing from 0 to 1, 1 to 0. That's important. For analog input, slightly different. You don't want every time the analog input changes to cause an event. That could be a lot of events. That's what we call chatter. So what we want to limit the amount of event on analog inputs. So we issue a deadband, which I'll talk about in the next slide. But if the point changes by a certain amount, it creates an event. And what you need to be aware about events in DNP3, especially on the DNP3 server side, is that whenever an event happens, that event point with timestamp goes into a buffer queue, event buffer queue. And it sits there until a DNP3 client pulls for it. And when the DNP3 client pulls for it, receives that event, and it sends back a confirmation, then that event gets cleared from the queue. If it does not receive a confirmation, that event stays in that queue. The third type is command type. So your output, your control, your binary input control, your analog output controls. So I talked about deadband, and you've probably worked with it plenty, especially if you're configuring a DNP3 server for your SCADA system. For your SCADA system to pull your data concentrator. And deadband is a set value, and this is used most common as a fixed deadband that you set to say, hey, if this point, analog input point changes by more than 10, create an event and timestamp it. And so, for example, if a value is from 5 and then jump up to 16 and the deadband's 10, so obviously the difference is 11, it creates an event. That event goes into a buffer queue. If that value of 16 goes to, let's say, 18, which is 2 units of 2, and the deadband set at 10, it's not going to create an event. So that's ignored. So that's how fixed deadband works. There's another type of deadband that's in DNP3 called integrated deadband. And this is a bit more complex, less commonly used, but not only the point has to change by a certain value. It needs to be times takes into play in the calculation. So if it changes by a value, a certain value over a certain amount of time, then it creates an event. So not very commonly used, but in the event that you need this for an application, integrated dead then might be something you need to look into. All right, within DNP3, you might see this a lot in a lot of DNP documentation. So if you are working with a device that supports DNP3, there's always what we call a DNP3 profile. Part of that profile will contain a object table. And what that is, and this is just an example of an object table within our own documentation, is, hey, this is the object, DNP3 object and variation that we support in this device. So I just want to go through some examples based on the points that we've talked about, different object and variation. So binary inputs, these are inputs. Here are object 1, variation 0 to 2. What that means is that if I'm a DNP3 client and asking for data, I can pull for object 1, variation 1. It means I'm asking for only the binary input status. I can ask for variation 2 and say, hey, I want your status value and with flag. And I'll talk about flag in the next slide. Or if I don't care what variation comes back to me, I can say, I'll just pull for object 1 variation 0. I don't care. And then the device will respond whatever its default is. So that's a binary static input. So binary input events has its own object group, which is object group 2 with different variation. And as I mentioned with events, there's usually with time associated with it. So you can have it, I don't want it with time, or I want it with a timestamp. And then there's relative time. With time, this is a big timestamp that reference whatever time that event happened, reference back to January 1st, midnight, 1970. So it's a big number. So that's a big amount of data used just to say what time it is. You can also do a relative time, which is used when the DNP3 server sends a time that it has to the client every so often, let's say 30 seconds or a minute. And the event that gets reported will be a relative time to that time that was sent. So it's a smaller value, takes up less space. It's just there's different variations to allow you how much data is being sent when you're polling. So you can pick and choose what you would like based on your communication network. Analog inputs. So these are your static again, is group object 30 in different variations. This could be your 16-bit, your 32-bit with or without flags. And again, this is static data, so there's no time considered here. And then for your events is your group object 32 with different variations. And if you want 16, 32-bit with time, without time, and so on. So we talked about flags. So flag is a 1 byte or 8-bit that comes with the data. If you, for example, you did variation 2 for binary input. And it allows the DNP3 server to provide more information about that point value. So for example, it could say, hey, this point value is online. Or if this bit's not set, it could say, hey, this is its current value, but it's actually offline in my DNP3 server device. Or if this point was locally forced, or there was comm lost. So it's just additional information about this point that the DNP server device can provide to your DNP3 client device. And then another common object and variation is class data. So group object 60 in variation 1 to 4 is your class 0, 1, 2, and 3 data. So this is what you can use to say, hey, I want to poll for class 1, 2, and 3 data, or when you're sending back the value, this is what I'm sending back. I'm sending back class 1, 2, and 3 data. We haven't talked about what these classes are yet, because that's where we're going to go into our polling scheme. As I mentioned, there's static data and there's event data. So you can poll specifically for static data, and you can specifically poll for event data, or you can do both. And so what the idea behind class 0, 1, 2, 3 is to prioritize these events or these static data. So static, sorry, you can't prioritize it. Static data just remains in class 0. That's where it stays. There's no, it's else about it. But for your event data, you can classify it being class 1, 2, or 3. I know this slide is very wordy, but the idea behind that is, hey, if you want your more sensitive information or critical information, you can specify that to be class 1. Your less important information will be class 2, and your least critical data can be class 3. Within DNP3 client side, you can, depend on your application, but you can have it so that granularly you can say, hey, pull class 1 data more often, so every 2 seconds, or class 2 data to be every 3 seconds. So really, at the end of the day, you just want to prioritize it so that your most critical data gets pulled more often and comes back sooner. So this is a big term in DNP3, is integrity poll. Integrity poll is when you do a class 1 event poll, class 2 event poll, and class 3 event poll, and then class 0 at the end. So every time you hear that, it means it's doing all of those polls in this order, though. The reason why it's in this order, obviously, as I mentioned, 1 is the highest priority, so you get those events first. The second medium priority, you get that second, and then last. And then why do you do a class 0 poll last? The idea behind that is the event that you're polling are something that happened in the past. Hey, these point changes based on deadband or binary status, it changed, it got time stamped, so I'm going to get those first. And then to end it all off at the end of an integrity poll, now that I have all the past events, I now want the most current value, which is my static data, which is what I always call a snapshot of your database. And that is the class 0 poll. For another type of, I guess it's not really polling because it's not polling, is unsolicited report by exception. Is when a DNP3 server device have an event and it can report that event right away. It doesn't need to be waited to be polled. So you can configure your DNP3 server device to do this. And you can have it so that it can accept a poll and do report by exception when the event happens. You can have it exclusively just do report by exception. So in the event that you're in a low bandwidth kind of communication network, an example of this is if you have a meter and a pole top in the middle of nowhere and you're talking radio and it's low bandwidth and you don't want, a polling every minute or every 30 seconds to kind of take up that bandwidth, you can just have it so that that meter only report the event whenever it happens. And otherwise that communication or that line is being unused. Obviously, there's some kind of heartbeat or to make sure it's still online, but just kind of lower the amount of data packet going through that communication. So the device can be configured so that it just sends event data when it happens and not wait to be polled. All right, so that's just kind of the high level, point-wise, polling scheme-wise. I hope some of the terminologies, is familiar to everyone, and hope it cleared up if you had any concerns about that or any questions. I know questions are coming in. I'll be answering them once I have a little break and when Brett and Jamie start demoing their section. So to dig a little bit more deeper, and this is becoming a little bit more bits and bytes kind of part of the presentation, and just to kind of let everyone have a better understanding what is happening in DNP3 when you're transmitting data and so with if you ever taken any protocol training, this OSI or Open System Interconnection model, 7-layer model comes up a lot. This is used to explain how data gets transmitted. So before data gets transmitted, it goes through these 7 steps where it kind of preps the data to get ready for transmission. And then it goes through these 7 layers, and then physical layers where you're actually sending the data. So it could be, you know, your communication network. And then when it receives it, it goes through those layers in the opposite direction to kind of remove those data so that it can kind of build it back up. So the message can kind of get breaks up, and then when it receives, it will kind of be built up again so that, you know, whoever the user at the application level can read that data. So that's the idea behind it. What they say is DNP3 only uses 3 of those layers, actually 4. And we use the physical layer, data link layer, transport, and application. And I'll go through these layers and what kind of additional information it adds to the data packet and why it's doing it. To explain the layers, we kind of created a real-world analogy. And so at the end of the day, you know, when you're sending a message, it's kind of like writing a letter to somebody. So let's say we have a client friend and a server friend. Client friend wants the latest news from the server friend. So, hey, what's going on with you? So that friend writes a letter. It could be a really long letter. So now it's on multiple pages, really needy, apparently. And so they write a letter. And when that letter gets, you know, organized into multiple pages, that's what the transport layer is doing. It's kind of organizing and sequencing those pages. When you put those letters into an envelope, you're kind of going through the data link layer. The envelope is, you know, you're wrapping it properly, you're putting the right format, you're putting your addressing on it, your return address, so on. And then physical layers, your transport. Hey, the mailman, the mail truck, whatever. How are you transporting it from you to your friend? And then when your friend receives it, you know, opening up that letter is the reverse effect of the data link layer. You're opening it up, you're prepping it to be read, and your transport layer is now in charge of making sure, hey, did I receive these pages in the right order, correlate it, and now that letter gets put in the proper order, and your friend can read it and actually understand what it says, and then respond back in that opposite direction. So hopefully that kind of put everyone in their head what really each layer does. It's mostly for, you know, correlating, sequencing, packaging to be ready for sending is the main jobs of these layers. So physical layer, I don't want to go into too much detail, is really just your method of communication. Is it your serial communication? Is it Ethernet, fiber optic? So this, you know, there are some settings related to these. These could be your baud rate for your serial, your IP address for Ethernet, your handshaking, all that is your physical layer. So how is data being transmitted through the physical layer? So I like this PowerPoint slide the best. When I was learning DNP3, this helped me visualize the most. So this could be your, you know, when data is ready to be sent, there could be a lot of data. And so data get organized in fragments. So I always think fragments a big word, so we think a big chunk of data. And it could be multiple fragments, but each fragment cannot exceed 2048 bytes or octets. And so it would be, if it's a lot more than that, then you can have multiple fragments. Each fragment will have an application header. So an application header is added to, so what we saw earlier is to allow sequencing of multiple fragments, so the order of it. And then your transport layer makes it a segment. So not only your fragment is 2048, it gets broken up even to smaller data packet, which is 249 bytes. and it adds a 1 byte of header, transport header to it. The multiple segments not necessarily will have the application header, only the first one. The other remaining one won't have it. It's just get broken up. And then for your data link layer, which now is your putting in an envelope, quote unquote, with our real world analogy, is prepping it to be sent. So this is where you put in your addressing here. Anyone who's seen a DNP3 data packet knows it always starts with hexadecimal 0564. We don't know why. Whoever invented DNP3 just used those 2 bytes to indicate it's the beginning of the data packet. The data link header will be added, and then CRCs. These are cyclic redundancy. There's a slide for this, but I always call them CRC. Apparently, I didn't memorize the acronym, but that gets added to the segments, and now this is what we call a frame. So this is what, so these kind of thing is what I call kind of an envelope. It gets ready to be sent. So what is in the data link header? So data link header is this red thing here. And idea of it is really to prep the data for transmission. It starts with 0564. It contains the length of the frame, so it's kind of prep the receiving device to know, hey, this is how much of data I'm sending in this data packet. Direction of the message could be, hey, it's coming from a client to a server or server to client. This is a primary and secondary message. So in DNP3, primary message is usually a message that initiates the conversation. So, hey, I'm requesting data. And then secondary message could be confirming that. Function code, so within the data link layer, there is a few function code. Is this, I'm resetting your link. As in, hey, I'm about to send you some data, let's reset and synchronize our communication. So within DNP3, you might see this a fair bit. There's a reset link function code that gets sent before sending actual data. Am I confirming a data? If this is the unconfirmed data, which could be, that it means you don't need a data link confirmation. So this just kind of provide explanation of what this frame is doing. And then your secondary message could be an acknowledgement to something, or not acknowledgement, or providing a link status. Within the data link header as well, there's obviously, this is your envelope, has your destination address, your source address, and CRC check. So really the data link is, just remember, its job is to make sure it gets from point A to point B and provide additional information of what this data frame doing. Cyclic redundancy check, there you go. That's what CRC stands for. So cyclic redundancy check is a 2 byte or 2 bytes of data that gets added in after the data link header and after every 16 bytes data after that in a frame. And what it is generated by a specific algorithm, and its job is to detect data corruption during a communication. Don't technically know how it does it or what the algorithm looks like. I'm pretty sure it's very complex, but its main job is to make sure it detects for data corruption. If data corruption is detected, DNP3's server will resend that data packet again. Transport header, this is that little small bit here to, as I mentioned, this is where you correlate your pages. And so really is 1 byte of data, 8 bits, and it really contains, hey, I'm going to tell you if it's a final frame or it's a first frame, and then it also contains the sequence number. So, if it's multiple frame, each sequence number needs to increment after that, so that the receiving device or the DNP3 client can actually put it in order when it receives it. Because if you are, during transmission, if you're in IP network-wise, data packet might be received in different order, depending on speed and so on. And so the DNP server device, client device, needs to, once they receive it, it needs to look at the sequence number to put it in the correct order. All right, application header. So application header, as you remember, is at the beginning of the big fragment. It might not be in every segment or frame, depending on how long the message is. And it's to indicate if it's the first fragment or final fragment. So same thing as transport header just to sequence the smaller frame data packet. The application, this is to sequence bigger fragment size, the 2048 bytes of data. Again, it contains additional information saying, is it a confirmation? Is it an unsolicited message? Within the application header, there's also function code. And we talked briefly about function code when we talked about controls. And this is where it's saying, hey, this is what I'm doing. Am I doing a reading? Am I doing a writing, a confirmation? The operates, select, operate, direct operate. So those were the control function code that I talked earlier. Within DNP3, there's a lot more other functions that you could be using. There's freezing, if you want to freeze a counter and then read it. I'm not going to go through the details of all the function codes, but this is where it says what is exactly this message is doing. And this is just for a request. So a DNP3 client requesting something, and it's saying this is what I want to be doing. Response, pretty shorter. It's saying it's responding, or this is an unsolicited report. This is a unsolicited response function code. So really, again, the application header or any of the headers is to prep that whoever is receiving it to say, this is what this message is doing. It's just prep. It's just allow the receiving device to know what the data is. All right, internal indication bits. You might see this a fair bit, and we'll see that in our NCD configuration. Is only in a response. So only in, let's say, a DNP3 server response to a client, and it can add in indication bits to provide more information. So along with the data that it's responding with, it can say, hey, I'm going to turn on these indication bits to say I have some events in my class 1 buffer or class 2 buffer. I need time, for example. I need a restart. So these are kind of additional requests for information that a DNP3 server can send to a client, and it takes up minimal space because these are just 1 bit each. Again, just allow for more information. So far, when we went through all these layers, remember, we're just prepping that letter, right, to be sent or to be received. And what the actual data is being sent or being requested is explained by what we call an object header. And that comes right after the application header in the data packet. And that object header, as you remember, will right away say the group and variation. We talked about this. Group and variation, saying, hey, I'm sending you, or I'm requesting group 1, variation 2, binary input with status and flag, for example. So it prepping you what this data represents. After that, in the header, will indicate a qualifier and a range. And this is a table that kind of summarizes in hexadecimal what this does, but in summary, what am I requesting or what data is coming back? And this is where your indexing comes into play. Am I requesting all points or all events, or am I responding all points or events? And if I'm responding at all, if I have continuous addressing, I don't need to provide an index point or an addressing point. You can request for a range of points. So, hey, I only want to read from 0 to 100, or I'm responding back with event from address 0 to 100. You can indicate the quantity of the data, or the quantity and the range. So the idea behind object header to say, hey, this is what I'm reporting back, and these are the points or addresses that I'm providing back with. So this brings me to a feature we added in NCD or Orion that is not necessarily part of the DNP3 standard, but we added it to help you. So you may already be using it and you're not aware, or you may have seen this and was like wondering what it is. Smart reading. Smart reading is it's in the event that you want to be a little bit more efficient in your polling. So if you have this disabled, event poll by itself is most of the time an integrity poll, class 1, 2, 3, 0. And what happens when you do a basic integrity poll is that the DNP3 server device will say, all right, well, these are all my events in class 1, 2, and 3, and class 0, and I'm going to send it all back to you. That's why the data packets are huge. And then when you receive it, you kind of have to parse out the data that you want and then put it into your database, your register. When you have smart reading enabled, is based on your input points list. So for example, this is 0, 1, 100, 102, and so on. When the Orion is pulling the device, it's requesting specifically events for those point address. It's not doing a kind of shotgun effect. It's actually specifically requesting events for those points. So when the data is coming back, it's specific data to those points, and then you don't need to parse out what you need and don't need. So when data is coming back, it's a little bit more efficient, smaller data packet. And so not necessarily you need this if you're, high-speed network and you don't worry about data packet clogging up your bandwidth. It doesn't matter. But again, in the event that you have lower bandwidth communication, you might consider using smart reading to kind of lower the traffic in your network. All right, so some troubleshooting tips. Based on my experience with DNP3, we're always aware that server and client always need to match up, right? So, so for troubleshooting, we always want to make sure this is the number one is the DNP3 address configured on your server and client matches up. There's always a server address that's configured on both sides and the client address. Some depending on the application, you might not need to be configured on the server side what client I'm reporting to, but you just need to double check your addresses. Remember in the data link header, there's the destination and source address. Those addresses, when you look at the data packet, you need to make sure those are, matching up in your setting here. Obviously, baud rate's always a big thing. I ran into recently where couldn't pull a device. The end user assumed it was 20,000. It was actually 20,001 for TCP socket. So double check these. And then IP address, obviously very straightforward. But I did run into this in the last couple of months. Everything matched up and we couldn't get any communication. Some DNP3 server device kind of errors out if you're asking for a point register that doesn't exist. So let's say if I'm asking for a binary input register 105 on a DNP's client side, and you're requesting that, and the server sees that and is like, I don't have a 105. Instead of saying, hey, you're asking for the wrong register, it just won't work. So not only your addressing needs to match up, your baud rate needs to match up, whatever. Make sure your point list should match up from your server side and client side, or at least whatever you're requesting exists on the server side. All right, communications. So another good troubleshooting tool, because I kind of talked about the data packet, I do like to show this, is within the Orion, most of you may already know, you can see and capture communications in any protocol on the MMI interface. Recently with distro 10, we've added this to the web UI, and this is what it looks like. And you can view live communications of what's going on. So for troubleshooting purposes, this is very helpful. You can see your destination source address here. You can see it's an event poll. Remember, we talked about IIN indication bit. You can see that this device is requesting time sync. So not only within this window, you can see the data packet And if you want to be able to dissect, the headers that we talked about today, you can. And confirm everything's working, but we actually do translate it for you to see to tell you what that data packet is exactly doing. This is an integrity poll, and then device is responding back with data. So this is a very helpful troubleshooting tool. Even if you don't understand what's going on when you view this, you can always download it, send it to our support team. Our support team are very savvy with DNP3. They can look at it and say, oh, yeah, this is wrong. So so be mindful that this now exists on your web UI. If you have older firmware, you can still use your MMI to capture your data traffic. All right, I did a lot of talking today. My apologies. There's a lot of information to present. That being said, we will go a little bit over an hour today. Feel free to drop off if you need to. We are still recording this. And then if you need to catch the end of it, we will be posting this video onto our Power community, and you can kind of view the end if you want. But that being said, I'll transfer it over to Jamie.
Okay, great. So I'm just going to try and connect some of the dots between some of the things you saw in the slide deck and where you find those options in NCD. I'll be setting up a client port. On my desk, I have an LX Plus acting as the client and an SEL 351S acting as the server. So first, I've got just a demo file named here. Everything's completely blank at the moment. My 351S does not have any Ethernet connection, so I'm going to be doing a serial connection on port 1 of my LX Plus. This is going to be a DNP3 client port. All right, so here's where you're going to start seeing some of the items that she had mentioned. Port name, we're just going to call this 351S client. Module name is defaulted to MDNP. That's just the driver on the Orion's flash drive that provides the serial DNP functionality. So you can actually make any changes to that. My client address I know is 5. My serial connection options, data bit, stop bits, parity, and baud rate. One thing I do know is my baud rate is 19200. And the only thing you have to look out for here is to make sure that these options match what's actually on your server device. The receive and transmit parameters. So if you look at G's analogy of sending a letter, these options are all just to make sure that everything is happening in the correct order and you're not stepping over data coming and going. So the interbyte time is, it's basically the delay time between incoming bytes. So once that time limit is exceeded, the message incoming is assumed to be over, and that's when the cyclic redundancy check is calculated. The only time I'd really think to change this is if you're using something like a radio that introduces larger time gaps in between bytes of info coming in. Warm up and warm down. So the warm up is the amount of time between asking for data and when the first byte is actually sent. And the warm down time is the amount of time between the last byte of data and the lowering of the request to send. Poll delay, that's the time between, so if you've got an incoming response, and you have an outgoing message, you don't want to overload that communication line. So often a poll delay is used to slow down a client before it sends something like an unscheduled control message. These are all defaults, and it's all really going to pertain to your specific server device and your specific system. But for now, the purpose of this example, I think we're good with all of these default settings. Change the baud rate to 19200. So I'll click accept there. Now you see I'm able to add a new device. So as I mentioned, I'm going to be doing a Schweitzer 351S. So I'll just use one of the default config files we have saved away. I'll give it a special name. I know that my 351S has a device address of 1. Response timeout and retries. So the response timeout is the amount of time that the server device has to respond with the requested information before it's either turned offline, or depending on how many retries you have, it'll give it 3 attempts until that device and all of those data points are marked offline, and that can either be due to no response or even a bad cyclic redundancy check if the two devices aren't agreeing. Enable unsolicited, that's one of the items that she had mentioned. So basically, if you have the box checked, the client device, in this case the LX Plus, is going to send an enable unsolicited message command, and if it is not checked, then the server device will not be able to send any unsolicited messages or event changes. Event polls. So I think she had mentioned this as well. That's just your standard event poll when a binary or analog either changes state or goes outside of its deadband. We also talked about smart reading enabled. That's where this checkbox is found. I won't talk too much on that, but yeah, as she mentioned, when it's checked, the client polls using multiple object variations and qualifiers that are specific to your input point list, which will populate in just a second here. And if not, our DNP client is going to pull the server device using a class 0 all data command. And you can see once you check the smart reading enabled, you've got some additional options. You can request 32-bit counters, 32-bit analogs, and also data without flags. I believe it was on one of the slides. Flags just provide some extra information regarding controls and status points and all that. So if you request it, it might be more efficient, but you are going to lose out on some of the data that's included in that flag octet. Controls, as mentioned before, select before operate, as opposed to a direct operate. Multi-pulse controls, I think this is part of older systems, and I'm not sure it comes up very often, but basically the long story short is when the multi-pulse is selected, the client will use the exact number of pulses it receives from its server port for control signals. If it's not checked, it just uses a single pulse. If you don't know what multi-pulse is, or if you do know what it is, it's probably because you use it, but I don't see that coming up very often. Internal indication bits set offline when trouble. So in the fragments that she was mentioning, there's a trouble bit. So you have the choice to either turn that device offline when it senses trouble, and it'll turn back online once the server device has fixed the issue, or it'll just remain offline. Sending time sync, that's just for the client device to send the time sync when the server device is requesting it. And right here you have your time zone, so make sure that all the devices in your system kind of match up. Manual polling, I'll just mention this briefly. I think we're maybe running up on time, but this is also kind of outside of the scope of basic DNP training. So smart reading and manual polling are not compatible. You can only have one or the other. This basically gives you the option to manually type in specific variants and objects it's a comma separated decimal number that specifies exactly what part of data you're looking to receive. We're not going to go into any examples of that, but just so you know that's there. If you do decide to use it, it's recommended that you work with one of our engineers to get that set up. And the last one here, the analog output type, that selects the type of analog output points that's used by the device. So you've got single, double, floating points, 16, 32 signed integers, and then the default here is int, which automatically switches between the N16 and 32 depending on the value of the output point. So I'm good with all these settings. We're not going to go into secure authentication parameters today. That's one of the items that's also beyond the scope of our basic DNP3 training. So I will, yep, and there it's given me. So we'll just have smart reading enabled for this one. We'll update the device. So I'm sure, hopefully everybody here is familiar with populating a point list. So we'll grab some analogs. We can also grab some of these binary points. So you'll see here, the points that I populated over, you'll see the point number, base 0 for analogs, and again for binaries. And in this integrity group, you'll see right now it's a default poll group. So the one section we haven't touched on over here is integrity poll groups. So you can add and subtract as many groups as you'd like. Good example of this is, say, analog points. So in the regular event polling, if you don't expect your analog points to go outside of deadband very often, but you're still interested in knowing what those analog point values are, you can create a separate poll group. So then if I go back to my inputs, I've now got analog points listed. So I can use the common attribute tool to populate all of these to my analog points, and then leave the binaries just as a default poll group. So at this point, we've got a client port set up. So I have gone ahead and populated this into my LX Plus. This is the same demo file that already lives in my Orion. So you'll see here, this is under the Devices tab. You can see the polls and responses. It's been running for about 2 hours now. Under Data Values, you can check the Inputs tab. And my 351S is not hooked up to anything, but we'll still get some values for the binaries. We get one for the A voltage here. And then lastly, as she mentioned before, you've got the View Comms helpful troubleshooting tool. And again, you can see all the object variation qualifiers, the event polls going on, time sync requests, etc. So that's just kind of a live view of what that communications channel looks like. And I think that covers it for the client side. I'm going to pass it over to Brett, who's going to be showing what you do with these data points once you get it from a server device and how you would use your LX Plus to serve that data up to a master.
Okay, thank you, Jamie. Okay, so I'm going to talk about quickly the DNP server module in NCD. This is the module we would use through DNP to, for example, send information from our Orion RTU and send it up to a SCADA client. So you'll see I already have, I kind of took Jamie's file where he left off. So I'm going to make a new port. I'm going to put it as a network since it is hooked up via Ethernet. And I'm going to configure a DNP server. So here, this basic port configuration is a lot like the client side. I would note that the only difference is I'm configuring it for Ethernet or network as opposed to serial. But we'll start here with the port name. You'll want to give it something relevant, and I'm going to call it DNP to SCADA, just a name we can remember it by. So we will call it that. Module name, again, Jamie mentioned, this is just a kind of a driver that our Orion uses, so that does not need to be changed. Now, the port number, the TCP port needs to be specified for an Ethernet network connection. That port by default is 2000, and if you add extra instances of these DNP3 servers, it will increment that port. It'll make it 20,001, 20,002. Each of the DNP server instances we have set up needs a different port number. Max connections, you would set this typically to match the number of devices that we're going to be using this module to send our data to. So in this case, we're just going to be using one DNP connection to send all of our information to SCADA. So we're going to use a max connections setting of 1. Now the setting with the idle timeout, this is the number of seconds that the device has to detect, or it has to be idle, or it doesn't receive polls before the Orion would consider it timed out, and it would open that connection for potentially another device to connect to it. The thing to note about that, now when the next poll is received from that device, it will reestablish that connection. But a tip, this setting should be a longer period than the client device's poll rate. because if not, every time it pulls, before it pulls, it'll time out. So that's just an inconvenience of the system. So by default it's 60. Of course, adjust it if you need to. The section here again is about secure DNP. Here's the settings for that, but we will not go into detail. Similar to what Jamie noted, that's kind of a more advanced application. The reservations can be helpful. You'd use reservations to restrict the client devices that can pull the devices that are on this DNP server port. So, you can use a reservation so that you only accept connections from a particular IP, or you can set it so it can only a particular client address can connect and pull, or that a given device can only get data from a particular DNP server address. And that's in the case where you have multiple RTUs listed on here with different server addresses. Default variations, this is a topic that she had touched on. Basically, you specify the formats. If you remember the series of slides that talked about binary, analog, counters, outputs, you can pick the format of the data response. And the main thing here was, there are flags, there are, you can have it with flags, without flags. And she had talked about that. The important thing, this is the case where, typically the request will come from a client and it'll ask for a specific one of these, in which case the device will respond, with that format. If it doesn't specify, or if it uses that code 0, which is basically its way of saying it doesn't care, this is the default that it will respond with in terms of the format of the response. So that is a summary of just the main screen here. I'll click add a new RTU. And again, same thing here with the description. We give it a name that we can recognize it by. Since this is the only connection that's going to be on this device, I'm just going to call it Orion RTU. And I will click accept. Address. This is the DNP address for this DNP server. And again, it should match the client side. Now, if you recall, Jamie had set his point, when he was setting up his DNP client, he set it to the address of 5. Now, we don't necessarily have to make the address 5, but for consistency's sake, let's go ahead and make it 5. Now, the event buffer. The event buffer size, and I guess the thing about the buffer, but in between polls, when there are points that change, up past its deadband, and I'll touch on deadband in a second, it prepares to send an updated value to the client. And this event buffer size is how many points can be shown, or how many changes of points can be shown, or can be included rather in that response to the poll. And now typically 100 is going to be okay. You may want it more, let's say either if if there are just a whole bunch of points you're sending across, or if there's a really long time in between event polls. Typically 100's good, just by your discretion, or if you find the event buffer is filling, if it does fill, it'll kick out the oldest events. So, by your discretion, you would be able to set this based on what's needed. Our default is 100. The internal indication bits. Now these will correspond to what Jamie was talking about. These bits, there's the kind of time sync bit, and on the server you can check the request time. If you do, you can say how often are we going to include a request for a time sync with the client device. So you'd specify how many minutes you'd go request a time sync. That is the purpose of these. Now the trouble bit, if you check that, what the trouble bit does, basically if the communication status changes, the RTU device will set a trouble bit in its response to a client. That would typically be a prompt to a client, and it'll force an integrity poll to get the values for all the points. We don't recommend using it typically because some client devices have trouble handling this trouble bit. So we don't recommend it for that reason unless there's a specific need and it does in fact work. But that option's right here. Data link confirm. When this is checked, the RTU requests a data link confirm response from the client. And typically, we shouldn't use that unless we know it's required by the client. And we have that unchecked as default. Message delivery only. This goes a little bit deep, but I will say it establishes this RTU as a virtual RTU, which essentially means it forwards messages from the client through this Orion, in this case, to a server device or an IED. So basically, you can kind of say it's passing through messages from the client to an IED. To avoid going into too much detail, I will say anyone interested in this, there's an excellent tech note. It is called DNP3 routing. If you go to our community, our customer community, and you search for DNP3 routing, you will find that document, and it'll give you more information on a virtual RTU. Next is time zone. Again, Jamie had discussed this, either local or UTC. Just make sure that it matches all your devices. It should either be, typically UTC or local. It's, they should match on all your devices. Application fragment size, she touched on this, but these are the number of octets or bytes. It's a maximum size of the message, and that should be dictated by your SCADA client if anything different is needed. In almost all cases, this is just fine. Now for events with time, when the client polls and it gives the variation 0, which is, as she mentioned, kind of its way of saying it doesn't care, you can check these to say if by default we send those event responses with time of the device included. So then, there are checkboxes for class 1, class 2, class 3. Pick the ones you'd like a response with time on. So the next few options here pertain to unsolicited responses. And the first thing to point out here at the bottom, there is drop downs that you can enable, either class 1, class 2, class 3. You can either disable them. You can enable unsolicited responses. Now, a note on that is it requires there's a bit from the client that'll come in. It basically declares that unsolicited responses are allowed or enabled from the client side, and this is where you'd enable them on the server side. And there's the same drop downs for each. Legacy is a special option. You almost certainly won't use it. The legacy, it kind of tweaks the unsolicited response functionality based on a very old, a 1990, 1990s vintage DNP spec. You're likely, as I said, not to use it. If you come up with a case where you may need it, it'd probably be with a very old client device. If you have questions about that, feel free to ask us. And then the application confirm timeout. That, when RTU sends an unsolicited response, it will look for a confirmation to come from the client. And if it doesn't receive it in this number of milliseconds, it will repeat sending that unsolicited message. And message retries is the number of responses, or rather the number of retries it attempts. And since in this case, unsolicited means it's not being pulled, the destination address is saying where this message is going in terms of the DNP address. So if the client is, let's say, DNP address 100, we would punch in 100 for 100. So that's all to say about that. Redundancy parameters, that's a little bit of an advanced topic as well. But one thing I can say about the redundancy, that's an advanced topic. I don't know that it's too commonly used. If you have questions about this, again, an advanced topic, you can reach out to us if you need an answer, or have questions about redundancy. So I'll skip that from now, for now. So again, secure, this is more security information. You'll see checking the box opens up about 20 different boxes here to add in parameters. We will skip this for now. Again, being an advanced topic. If you have questions about it, let us know. We'll respond to you offline. I'll go ahead and accept changes on that. And now I'll show you briefly. Jamie did already show you on the client side. It'll be similar here on the server side. Move the points over. These are the DNP point addresses, and of course, these need to match between the server. They also need to match the client side. These class drop downs here is, classes 1, 2, 3, or 0. Now the deadband, let me pull some analogs over to show you. So that what the deadband means is if this point in between poles changes by, let's say if the voltage changes by more than 80 volts between poles, this point and the change will be entered into the buffer. When the next event pole comes, it will shoot this change over to the SCADA. So that's what the deadband does. It's how much a value has to change before it gets sent over. Now, in the case of, say, current, 80 may not make too much sense if we want to say maybe 10 instead. You want to make it so it makes sense for the point. And you'd use your discretion there. Maybe there are requirements handed down from your SCADA client. Min and max values also, this is pertains to scaling of the points. You'll have scaling on points coming in from the IEDs, and if you'll take this around in your Orion and shoot it to the SCADA, you may be able to leave these just the way they are. You may also have to tweak the scaling, to make it, I guess, to make the values go into your SCADA client, in kind of the correct range. We could go a lot into scaling, out of the scope, unfortunately, of this class, plus we're running late on time. But we do have excellent resources on scaling, including in our NCD documentation. So if you want more information on that, feel free to look that up or let us know. Same thing goes here for outputs. We will shoot these over. Again, it's the same idea, and I failed to mention there's the different point types. You can select the type of point. It does a pretty good job selecting the point type as default, but you can choose that from the list here. Again, DNP point addresses for outputs works just like inputs, and then if it applies, we don't have any analog values here, but you have the min and max values. And again, they work the same way. So that is just a quick run through all the screens of setting up a DNP server, and that's for say, an Orion device that would shoot data to a SCADA client. So with that said, is there anything else that we'd like me to show straight away, or would you like me to go ahead and go into the close?
I think we're good for now. Any questions asked, we will be providing the answers in a post-webinar email. So look out for that. Usually comes out about a week after, so sometime next week.
Okay, excellent. So with that said, we will wrap up this webinar. It is 15 minutes after the hour, so apologies, it did run a little bit long. The customer community, you will see a couple months ago, we did integrate our customer community into our main NovaTech automation website. This is just what it looks like now. There's the same search bar. You can search for any of the material that we have archived, including our old Power Hour webinars. There are a few links here with some helpful ways to reach out to us, including this link here. It's right front and center now saying book a call with an application engineer. If you click that link, it will take you to this page, this familiar page where you can select a date and time, select the time of day, and you can choose a member of our staff if you'd like to have a meeting, short, maybe 30-minute session with us to discuss a particular topic. If you click the drop down here, you can select anyone if you don't have a preference. If you'd like to choose, to request one of us specifically, you'll see this list here on the right. You can choose any of us from the drop down. And we have a relatively new member or two that are on this list. You'll see Ben Gradsky, recent addition to the team, very sharp. Shane Singleton is also on here, who's been around a few months, but any of us you can select from this drop-down list. So with that said, here's contact information for Chi, Jamie, and myself. And I'd like to thank everyone for attending. And everyone, if you have any questions, feel free to reach out. And otherwise, have an excellent day. Thank you.
Thank you, everybody.